Welcome to the Deep Dive. We're your guides, and what we do is take these really complex stacks of documentation, research papers, technical specs, and we boil them all down into the architectural knowledge that you actually need.
That's right. We're all about turning those, fuzzy concepts into something that's crystal clear and, more importantly, actionable.
And today, we are tackling really the heart of modern enterprise infrastructure.
The data analytics stack.
Exactly. And this isn't going to be just a list of tools. This is a deep dive into the engineering philosophy behind processing petabytes of data and doing it efficiently and cost-effectively.
Yeah, and for a lot of you listening, you probably already know the names. You've heard of BigQuery, Dataflow, Dataproc. But our mission today is really to solidify those intermediate concepts.
The ones that people kind of get, but not really.
Exactly. We want you to walk away understanding the critical trade-offs, the why behind choosing one tool over another. This is that second, more detailed look into the data universe.
That's a great way to put it. So we are zeroing in completely on the data analytics section of the cloud ecosystem. Our source material for this is a really rigorous stack of documents covering these complex decision points.
And we're going to synthesize all of that into a clear roadmap. We'll be focusing on BigQuery, of course, but also stream processing, some really key optimization techniques, and the role of visualization.
Okay, so let's unpack this. Let's start right where every big data project begins.
Storage.
Storage. And the fundamental distinction in how we analyze data at, well, true cloud scale.
Let's do it.
So when we talk about enterprise data warehousing in the cloud today, the conversation pretty much has to start with BigQuery.
It's the inevitable starting point, yeah.
Our sources confirm it's become this default choice for anyone needing massive analytical power. So why? Why has BigQuery become so ubiquitous for these multi-petabyte data sets?
Well, it really comes down to one word, specialization. BigQuery is the Google-recommended, really optimized tool for something called online analytical processing, OLAP. And to really appreciate its power, you have to compare it to the systems it's usually replacing, or at least complementing.
Which would be OLTP system.
Exactly. Online transaction processing. Think about your traditional relational database like Cloud SQL. These systems are designed for transactional speed.
So recording a single sale or updating a single user record in an app.
Precisely. Their strength is consistency, immediate feedback. They handle thousands, maybe millions, of these really small, fast writes and reads.
Okay, so if I'm using that analogy, an OLTP database is kind of like the dedicated express lane at a grocery store. It's totally focused on these rapid, small transactions.
That's a perfect analogy.
But what happens when you try to run a huge, complex query in that express lane? It gets bogged down really fast, doesn't it?
It absolutely does. An OLTP database has to scan across these highly structured rows, and it just cannot handle the sheer scale of the questions you want to ask in an analytical context.
And that's where BigQuery steps in.
That's exactly where BigQuery and OLP step in. BigQuery is built for massive, complex queries, for aggregations, for reports, across hundreds of terabytes or even petabytes of data.
How does it do that? What's the secret sauce?
It's built on what's called a columnar architecture. It stores data in columns, not in rows, and that's perfect for analytical jobs that might only need to look at, say, 2 or 3 specific fields across billions of records.
So it doesn't have to read the entire row for every record. It just grabs the columns it needs.
Exactly, and that saves a tremendous amount of processing. BigQuery, then, is the data science lab. It's not designed for the speed of the immediate sale, but for that complex, long-running research across the entire history of sales.
It prioritizes analytical throughput over that transactional speed.
That's the key, and our sources are really explicit here. If you are building massive marketing analytics platforms or reporting tools that operate on that hundreds of terabyte scale, BigQuery isn't just an option, it's pretty much the mandatory choice.
And there's another point that the sources make, which I think is crucial from an adoption standpoint. It's about the interface.
The SQL interface.
The familiar SQL interface. If a company is migrating their whole data architecture, they probably have a team of business analysts, data scientists, people whose entire institutional knowledge is rooted in SQL.
And that familiarity is a huge, huge accelerant for adoption. Imagine the alternative. You have to retrain hundreds of analysts on some brand new proprietary querying language just because you needed to scale. It would be a nightmare.
Right. BigQuery just completely eliminates that barrier.
It does. You get to leverage the power of cloud-native petabyte-scale analysis, but you don't have to abandon standard ANFI SQL. That dramatically flattens the learning curve and just reduces the migration frictions so much.
So it's that combination of massive power and a familiar, accessible front end that makes it the winner in the enterprise data warehousing space.
That's why it wins.
Okay, so that's scale in terms of volume. Let's talk about a different kind of scale. Speed or velocity. BigQuery is great for that long-term structured analysis, but what happens when the data is arriving faster than any warehouse can structure it?
This is a fascinating scenario that our sources detail. It's about managing click data from a large portfolio of websites.
And the numbers are pretty staggering.
They are. So the scenario involves a typical rate of about 6,000 clicks per minute, which is fast but manageable. But then they experience these bursts.
Bursts that reach 8,500 clicks per second.
And that surge traffic is the definition of high-velocity streaming data. Your standard SQL databases, they just can't sustain that kind of ingestion rate and burst handling. They just fall over.
8,500 per second. That's not a stream, that's a tidal waves of data. So if the traditional relational databases just buckle under that pressure, what infrastructure is purpose-built to handle it?
For that, we turn to Google Cloud Bigtable.
Bigtable.
Bigtable is a fundamentally different beast. It's a wide-column NoSQL database. It's optimized for two things: high throughput and low latency access.
So what does it give up to get that?
It gives up the rich relational structure and the complex analytical queries of SQL. It sacrifices that in favor of raw ingestion speed and the ability to serve up data really quickly for operational lookups.
So if we stick with our analogy, BigQuery is the analytical warehouse, perfect for that deep analysis you do once a month.
Yeah.
Bigtable sounds like the high-speed sorting facility at the front of the building.
That's it. It's capable of handling those continuous, massive arrivals, the 8,500 clicks per second, and serving up those raw events with minimal delay. It's focused entirely on getting the massive volume in and serving it out quickly for simple lookups.
And that's the critical distinction then.
It is. Bigtable solves the operational storage problem for high-volume, time series, or streamed data. You see it a lot with machine-generated data, IoT sensor streams, or those click logs.
And BigQuery handles the complex analysis after that data has been processed or aggregated.
Exactly. They're both optimized for massive scale, but their specialty and therefore their ideal use case is completely different. One is for operational speed, the other for analytical depth.
That makes the architectural choices very, very clear. But before we can even get to the analysis, we have to talk about a really messy real-world problem.
Yes. Data quality.
The source materials address this challenge of moving what they call degraded or poorly maintained data from these legacy on-prem systems into the, beautiful, clean cloud.
Garbage in, garbage out, right?
Absolutely. Data migration, I imagine, often exposes years and years of undocumented inconsistencies, missing values, formatting errors.
All the skeletons in the closet come out. And if you just dump that data directly into BigQuery, your entire analytical effort is going to fail before it even starts. The results will be worthless.
So we need a dedicated prep phase.
We do. And the first step is just to get the raw files out of that legacy system and securely into the cloud.
So we upload them to cloud storage. We're establishing our raw data lake.
That's the landing zone. Cloud storage acts as this immutable repository for the raw, untouched data. But for the actual work of exploring, cleaning, and transforming it, the best practice recommended by our sources is a tool called Cloud Data Prep.
Okay, why Dataproc specifically? I mean, couldn't a data engineer just write a Python script in a notebook to clean the data?
They absolutely could. And for some really complex transformations, they still might. But Data Prep serves two really important purposes that a simple notebook might miss.
Okay, what are it?
First, it's visual and it's guided. It sort of democratizes the cleaning process. An analyst who might not be a Python expert can visually explore the data set, spot anomalies like inconsistent date formats or incorrect column types.
And they could apply transformations through an interface, not through code.
Exactly. Through an intuitive UI. And second, and this is really important, it generates transformation recipes. These are repeatable sets of steps that can be reliably run at scale over and over again.
So the aha moment here is that Data Prep takes the data prep burden off the core engineering team. It provides a specialized visual tool for improving data quality and defining these transformation workflows before the data even gets loaded into the warehouse.
That's it. It's all about efficiency and best practice for handling that messy legacy data. It minimizes the time you spend wrangling data and maximizes the time you spend analyzing it.
Okay, so we've established the foundation. We know where the raw data lands, which is cloud storage. We know how we clean it with Data Prep. We have the high-speed operational store in Bigtable and the analytical powerhouse in BigQuery,
A solid foundation. Now we can move to the engine room.
the processing layer.
Let's get into it.
So the comparison between Dataproc and Dataflow. This is arguably the most common architectural decision point in this whole stack, and for an intermediate listener, this one can often feel pretty fuzzy.
It really can. They sound similar. They both process data at scale. It's easy to get them confused.
So let's try to make the distinction definitive. And it seems to come down to one primary question. Do you have existing code, or are you building a new unified system from scratch?
That is the perfect way to frame it. Let's start with Dataproc. When should you use it?
The sources say it's when a company is forecasting a sharp increase in existing Apache Spark and Hadoop jobs.
Existing is the key word there. And they want to scale this demand with the least amount of operations work and, critically, the least amount of code change.
So Dataproc really exists to honor the institutional investment that a company has already made in the Hadoop and Spark ecosystem.
Exactly. You don't want to toss out a decade's worth of highly complex proprietary data pipelines just because you're moving to the cloud. That would be a massive undertaking.
So Dataproc lets you lift and shift.
It's the ultimate lift and shift tool for that ecosystem. It handles the immense administrative burden of managing Hadoop and Spark clusters, all the provisioning, monitoring, patching, scaling. But it maintains compatibility with your existing code and your ecosystem tools like Hive or Pig.
This is where that analogy from the source material comes in. Dataproc is like moving an entire complex industrial kitchen.
A very high-maintenance industrial kitchen.
Right. And moving it into a fully serviced cloud facility. The facility takes care of the building maintenance, the plumbing, the electricity, all the infrastructure.
But your chefs still get to use all their same highly customized tools and, more importantly, their same recipes. You get the benefit of cloud scale without that incredibly painful rewrite.
And that infrastructure management leads directly to some pretty immediate cost optimization opportunities.
It does. Our sources highlight a really key cost-saving strategy, especially when you're migrating those existing Hadoop jobs, specifically batch jobs that can tolerate a bit of interruption.
And that would be using preemptible worker instances.
Preemptible worker instances. This is a game changer for batch processing costs.
So you get these huge cost savings. We're talking 70–80% off the standard price. But the catch is that you risk the instance being terminated with very short notice.
And that trade-off is crucial. For large-scale batch analysis, like a weekly marketing attribution job, where restarting the job only means losing a few minutes of processing time.
It's a no-brainer.
It's an absolute winner. And Dataproc makes managing and orchestrating those interruptible workloads really seamless. It turns that cost risk into a massive financial advantage for the company.
Okay, so that's Dataproc, preserving the past while scaling for the future.
Now, let's pivot completely. What if a company is starting fresh? Or maybe they've realized their existing architecture with one system for batch and another for streaming is just too cumbersome.
That is the domain of cloud Dataflow. Dataflow is the definitive choice when your analysis demands a unified approach.
A mix of both batch processing on historical data and stream processing on live data.
Exactly. If the team doesn't have any existing Spark code, or if their number one priority is a fully serverless, zero infrastructure management solution, then Dataflow wins hands down. So Dataflow is about building the most flexible, modern pipeline you can. What's a fundamental technology that allows it to unify batch and stream like that?
It's all based on Apache Beam.
Okay, explain Beam.
Beam is the programming model that, well, it treats batch data, which it calls bounded sets in streaming data, or unbounded sets, using a single unified paradigm. This is a huge simplification for development.
So instead of writing two completely separate pieces of code or trying to force your streaming engine to pretend it's a batch engine,
which never works well,
you just write one pipeline, one piece of logic, and it handles both historical data and live streams seamlessly.
That's the power of Beam. So if Dataproc is the industrial kitchen using old recipes, Dataflow is the fully automated, highly flexible conveyor belt system.
I like that. It handles a continuous stream of raw ingredients just as easily as it handles a massive dump of historical ingredients, and it uses the exact same processing logic for both.
And the conveyor belt itself, the system, it manages all the machinery and the scaling for you automatically. That's the serverless part.
And that serverless nature extends to some really sophisticated use cases,
Yeah.
like building machine learning features.
It does. Our sources lay out this great scenario where you're building a recommendation engine.
Hmm.
You need to do structured processing, but you also have to store the raw, unstructured data in a cloud storage bucket for later reprocessing,
Why would you need to reprocess it later?
in case the source structure changes, or, more likely, you develop a better algorithm for processing it.
Ah, so data flow and cloud storage work together to create this really robust data lake architecture.
They do. You use Dataflow to read the raw data from the bucket, process it into a structured format, maybe for BigQuery, but the original raw source file remains untouched and immutable in the bucket.
It's like a safety net.
It's the ultimate safety net.
Right.
If 6 months from now, the upstream source changes its schema or you invent a better processing algorithm, you don't have to panic. You just point your Dataflow pipeline back at that raw source data in the bucket and reprocess the entire history with the new logic.
That is incredibly valuable flexibility. Okay, let's move to the real-time element here. How do we actually handle that stream of data before it even hits Dataproc or Dataflow? We need some kind of messaging infrastructure to deal with chaos.
Chaos is absolutely the right word, because when you have multiple producers, websites, payment gateways all sending data, and then you have multiple consumers processing pipelines, monitoring tools, all needing that data, you have to decouple the system.
So if you have a stream of user-click events, you need to be able to absorb those traffic spikes and support what's called a many-to-many fan-out.
You do. You need middleware for that.
And that middleware is Cloud PubSub.
PubSub is essential because it acts as a buffer. It's a globally distributed message queue. It allows those fast-moving producers to just dump their data quickly and move on, while the slower processing consumers can ingest that data at their own pace.
So if a consumer goes down for a few minutes,
PubSub just holds the messages in the queue until it comes back online. That separation is the absolute key to architectural resilience and scalability in a streaming system.
but wait, PubSub is just the transport layer, right? What happens when a client needs true data integrity? The sources mention this really tough scenario. A legacy streaming API that expects events in strict chronological order with no repeat data.
Ah, yes. Guaranteed once. First in, first out delivery. FIFO.
That sounds really hard to do in a massive distributed system.
It's incredibly challenging because PubSub on its own, it guarantees at least once delivery, but it doesn't necessarily guarantee strict ordering across all consumers or single instance delivery under every possible fault scenario.
So to enforce that guaranteed once FIFO, you need more than just PubSub.
You do. The architecture has to combine Cloud PubSub with Cloud Dataflow.
Okay, so what is Dataflow doing under the hood to handle that sequencing and deduplication when, like you said, distributed systems are fundamentally chaotic?
Dataflow is leveraging its Apache Beam model for what's called stateful processing. It implements these really sophisticated techniques like windowing and watermark tracking. So it uses its own internal state management to detect and discard any duplicate messages. And more importantly, it can buffer events temporarily, sorting them by their event timestamp before it emits them to the next stage. It imposes the required chronological order on top of the raw stream from PubSub.
So PubSub gets the data from A to B efficiently and handles the scale, but Dataflow provides the processing intelligence to clean up the chaos, enforce the order, and ensure those delivery guarantees.
You need both for high-integrity streaming, absolutely.
Okay, one last scenario in this section. Migration. Real-time replication from a legacy database into BigQuery. Say I've got an on-premises Oracle database, and I need to replicate all the changes, inserts, updates, deletes into BigQuery for a live dashboard.
And you want a serverless solution without having to build a complex custom data flow pipeline.
Right. This sounds like a surgical requirement for what's called Change Data Capture, or CDC.
It is. And for this, the specialized serverless solution is a product called DataStream. DataStream is designed specifically for this. It monitors the source database logs from Oracle, MySQL, and others for transactional changes, and then streams those changes directly into the destination, in this case, BigQuery.
That sounds incredibly convenient compared to building a custom CDC pipeline from scratch.
It's much faster and easier to set up for pure replication. It's serverless, it's mostly point-and-click configuration.
So what's the trade-off? When would I still choose to build a custom pipeline with Dataflow?
You'd choose Dataflow if your replication needs involved complex transformation or enrichment or applying custom business logic during the replication process itself.
Like masking certain fields or merging data from other sources on the fly.
Exactly. DataStream is the right choice when you just need a high-fidelity, real-time mirror without that custom processing. It's the fast, simple mirror. Data flow is the custom processing factory.
Okay, that makes perfect sense. We've now covered the entire data journey from ingestion to processing. Now we've got to move into the highly technical, but super important domain of optimization and security. This is where every decision directly hits the bottom line.
This is where you save the money. Let's get into it.
All right. This next section is so critical, especially for an intermediate audience, because optimization in BigQuery is a direct reflection of cost.
A very direct reflection.
BigQuery's pricing model is heavily based on the amount of data scanned per query. So our sources present this classic optimization challenge. You're analyzing 10 petabytes of data. There's a column, userid, that's used constantly as a filter. The goal is to minimize cost, meaning bytes, scanned, and improve performance.
This is the bread and butter of a BigQuery architect, and the challenge is solved by leveraging BigQuery's columnar storage architecture through the combined use of partitioning and clustering.
And the optimal structure, according to the sources, is to partition by date and cluster by userid.
That's the one. Let's spend some real time on this to make sure it's solid for everyone.
Okay, let's start with partitioning by date. Let's use that filing cabinet analogy from the sources. What does partitioning achieve?
So partitioning by date acts as the coarsest, most powerful filter. Imagine you have 10 petabytes of data that's accumulated over 10 years. Partitioning effectively divides that one massive table into smaller, separate physical storage segments based on the date field.
So you have a drawer for January 2024, a drawer for February 2024, and so on.
Exactly. You have thousands of drawers in your filing cabinet. Now, when a query comes in that only needs data from the last quarter, BigQuery immediately knows it can just skip scanning the other 9 years and 3/4 of data. It doesn't even open those drawers.
So partitioning dramatically reduces the search space right from the start. That saves immense cost immediately just by eliminating irrelevant years or months from the scan.
A huge saving. But the query still filters heavily on userid. So if our query is running only on the last month partition, only on that one drawer, how does clustering help inside that partition?
This is the next level of optimization.
It is. Clustering is about the organization within the drawer. So inside the March 2024 drawer, the data blocks are physically sorted based on the clustered column, which is userid.
So all the data for user A is together, then user B, and so on.
Exactly. And BigQuery knows the physical layout of those data blocks. It knows where user A's data starts and ends. This means BigQuery doesn't have to read every single data block in the partition anymore.
It knows, based on the userid filter in the query, exactly which specific blocks contain the data it's looking for.
Precisely. BigQuery leverages that clustering metadata to perform what's called block pruning. It just skips reading entire storage blocks that don't contain the targeted userid.
Wow. So since billing is based on bytes read, combining partitioning, which skips entire months, and clustering, which skips unnecessary blocks within those months, is the single most powerful thing you can do to maximize speed and minimize cost.
For massive analytical tables, it is the #1 architectural decision you can make.
That explains the mechanics perfectly.
Yeah.
Okay, let's transition from cost optimization to governance, specifically handling personally identifiable information, or PII, and all the regulatory compliance that comes with it.
A huge topic. And let's start with a mandatory dilution scenario. Current legislation, like GDPR or CCPA, often requires deleting specific data upon request. The source example is health data, like sustained injuries, for members between certain ages.
And since this requires the total eradication of specific records, the solution has to be definitive. There's no room for error.
No, there isn't. And BigQuery fully supports DML, or data manipulation language. So the solution here is to use a unique identifier for each individual, and upon receiving a legal deletion request, you execute a delete statement to remove all rows from BigQuery associated with that identifier.
Clean, simple, and definitive. It meets the compliance requirement.
Exactly.
Now, for a more complex scenario, access control. Let's say we need to share non-PII data with a data science team, but we have to ensure that the PII things like injury details or names is only accessible to the compliance team.
And critically, we want to avoid creating duplicate data sets, which is a maintenance nightmare.
Right, so how do we do that?
This is a perfect use case for authorized views. It's a multi-layered security model. First, you need architectural isolation, so you create a separate data set specifically for the data science team.
Okay, a new container for them.
Second, you create SQL views within that new data set. And these views are written to explicitly exclude the sensitive PII columns from the underlying source tables. The view is basically a saved query that only selects the safe columns.
But if the data science team queries that view, the view itself still needs to access the source data, which contains the PII. How do we make sure the data science team doesn't somehow gain direct access to that source dataset? That feels like a potential backdoor.
That is the crucial and often missed third and fourth step. You must authorize the view to access the source dataset. This creates a secure tunnel.
So you're giving the view permission, not the user.
Precisely. The data science team is only granted IAM roles to query the view, for example, the data viewer role on the view's dataset. The view itself is granted access to the sensitive source data, allowing it to execute the query. But the user never interacts directly with the PII columns or the source table. The view acts as the security enforcement layer.
That is a really robust governance model. It maintains a single source of truth while strictly segregating access based on policy. Very cool.
That's the recommended best practice.
Okay, let's move to operational oversight. Auditing and monitoring costs. If a company's compliance team needs an audit to see exactly how many queries each user ran in the last month, where is that information recorded?
That information lives in the platform's operational logs. To get it, you have to use cloud audit logging. The necessary action is to go into those logs and filter them specifically on the BigQuery query operation to extract the user, the job ID, and the timing information for your audit.
So that covers historical auditing. But what about real-time cost control in a pay-per-use environment? If I need to monitor right now which queries are consuming the most resources and which users are generating the highest costs, what's the advanced strategy for that?
For that, you need to apply BigQuery's analytical power to its own operational data. It's a bit meta.
How does that work?
The solution is to create a cloud logging sink. This sink exports the BigQuery data access logs back into a structured BigQuery table.
So you're turning the service logs into a data set that BigQuery itself can then analyze.
Exactly. Once those logs are structured and queryable within BigQuery, you can run standard SQL analysis on them just like any other business data. This lets you easily rank queries by bytes scanned, calculate user spending, and identify rogue or poorly optimized jobs in near real time. It provides that granular cost control that's so necessary in large environments.
That's a powerful feedback loop. Okay, let's delve even deeper into advanced security. First up, external key management. If a highly regulated company mandates that they have to generate and manage their encryption keys outside of Google Cloud, how is that implemented for sensitive data in BigQuery?
This is a big requirement for data sovereignty and control. It's often achieved with something called customer-managed encryption keys, or CMEK, or in this specific case, an external key management service, Cloud EKM.
And the process is very specific, I assume.
Highly specific. First, you must import a key into Cloud KMS, since the key is generated externally. Then, when you're creating the BigQuery dataset, you have to use the customer-supplied key option and select that specific key you just imported.
So this means the actual cryptographic material needed to decrypt the data is fundamentally controlled outside of the cloud vendor's domain.
That's right. It meets the strictest regulatory requirements, even though the data resides in BigQuery. The company maintains full control over the encryption mechanism.
Control is paramount. Now, let's consider the data exfiltration risk. A company has a hybrid environment connected via VPN. They're worried a malicious insider or compromised code could leak data from BigQuery back to their on-prem network or out to the public internet. What establishes the digital moat here?
Yeah, this is a huge fear. We've all seen security mechanisms fail when a legitimate credential gets stolen. You need a perimeter defense that doesn't care about IAM rules if the access point is outside the boundary.
And that's where VPC Service Controls come in.
Exactly. You have to configure VPC Service Controls and also configure private Google access. VPC Service Controls establish this secure perimeter around high-value services like BigQuery. And this perimeter ensures that data can only be accessed or moved by authorized identities from within the defined network boundary.
So even if someone steals a user's IAM credential that has full access to BigQuery, if they try to use it from an external, unauthorized IP address,
the VPC Service Controls perimeter blocks the access attempt entirely. It prevents the exfiltration of your 10 petabytes of data. It's a network-level zero-trust boundary.
that's a crucial layer of defense, especially in those hybrid environments. Okay, one final IAM question. Centralized billing control. Let's say data lives across multiple projects, say Project A and Project B, but all the query costs have to be billed to a single separate project, Project C. What roles does the user need?
This is a common pattern. It separates the ability to read data from the ability to generate cost. The user must be granted the BigQuery job user role on the billing project, which is Project C.
The job user role. And what does that let them do?
That role allows them to run jobs and queries, and because they're running the job through Project C, that project is the one that incurs the cost.
Okay, but what about actually accessing the data over in projects A and B?
To do that, they need the BigQuery data viewer role on the projects that actually contain the data, so on projects A and B.
Let me see if I've got this. The data viewer role is like the key to read the books in the library, which are in projects A and B.
Perfect analogy.
And the job user role on project C is the money to pay for the photocopying or the query processing. So you can read the books in A and B, but the bill for all the computing goes to C.
That is a perfect explanation. It's a clear and robust separation of concerns, ensuring financial accountability stays centralized.
Awesome. We've covered storage, processing, optimization, and governance. Now let's tie these massive components together.
Let's complete the picture.
Okay, we established earlier that Cloud Bigtable is the optimal storage for that high-volume, high-velocity ingestion, like IoT sensor data.
Right, the operational store.
And BigQuery is the master analysis engine. So what happens when the data science team needs to run complex, ad hoc SQL queries and aggregations for their monthly reports against that live, massive volume of operational data that's sitting in Bigtable?
This is such a classic scenario. You want the analytical flexibility of BigQuery, but you don't want the operational burden of trying to migrate petabytes of historical data out of Bigtable just to analyze it.
That would be a nightmare.
It would be slow and expensive. So the most efficient architectural pattern here is to use federated queries. Specifically, you use BigQuery to query the data directly in Bigtable by defining it as an external data source.
So BigQuery acts as a command center. It sends a query over to Bigtable. Bigtable processes the low latency lookups that it's good at, returns the necessary subset of data.
And then BigQuery uses that data for its complex SQL aggregation. It's doing the heavy lifting of the analysis. This avoids a slow, costly, and resource-intensive ETL process.
You leverage Bigtable's specialty for storing and serving massive operational data rapidly, and BigQuery's specialty for running full standard SQL analytics.
It's a highly efficient hybrid approach. It ensures the data scientists can use the tool they know, which is SQL, against the data right where it lives.
Okay, but are there any performance caveats to this? Is a federated query always as fast as querying data that's natively stored inside BigQuery?
That's a great question. No, there are trade-offs. While it's incredibly convenient for that ad hoc analysis, federated queries typically perform best when you're querying a subset of the data.
So if the data science team needed to analyze every single record and do some massive petabyte-scale join,
then moving the data to BigQuery natively would still be the fastest approach. But for that targeted ad hoc analysis against the Bigtable operational store, federation is the clear winner for efficiency and just speed to insight.
that makes sense. Okay, let's focus on the final mile, turning all this analyzed data into trustworthy business insight. And this brings us to visualization and the concept of a semantic modeling layer.
This is such a critical piece. The problem so many companies face is consistency, what our sources call dashboard drift.
I've seen this. Analyst A defines monthly active users one way in their dashboard.
And Analyst B, on a different BI tool, defines it just slightly differently with a different filter. And then the CFO looks at two dashboards and gets two completely different answers for the same metric.
And trust in the data just evaporates.
It completely evaporates. And that trust deficit is a massive organizational hindrance.
So we need a modern business intelligence, or BI, platform that's specifically designed to eliminate that drift with all the data residing in BigQuery.
And that product is Looker. Looker is designed to work seamlessly with BigQuery, and crucially, it enforces that consistency through its unique language, LookML.
Okay, tell us more about LookML.
Sure.
Why is defining a metric in LookML so much better than just writing a really robust SQL query in a normal dashboard tool?
Because LookML is a proprietary semantic modeling language. It allows the central data team to define every single business metric, things like revenue, active user, lifetime value, once centrally in the Looker environment.
So it creates a definitive source of truth for the logic.
It does. So when an analyst goes to build a new report, they don't write the metrics logic from scratch. They simply reference the predefined LookML measure.
So Looker isn't just a prettier dashboard interface, it's actually a governance layer for the metrics themselves.
It absolutely is. It ensures that the business logic is identical across every single report, regardless of which department or which analyst runs the query.
So if the definition of active user changes,
The data team updates one lookml file, and every single dashboard across the entire company updates instantly and consistently. That assurance of data integrity is the massive win for the enterprise. It solves the dashboard drift problem.
we've now hit all the individual components, from high-speed storage to unified processing to metric governance. Let's close out with the ultimate synthesis scenario, a complex, real-time analytics stack.
Let's put it all together.
If a company needs a complete pipeline for real-time fraud detection, which tools fit together and why?
Okay, this stack requires maximum velocity, low latency, and guaranteed processing fidelity. We need all the tools we've talked about working in concert. Let's walk through the data flow.
All right, start with the source. Transaction data is streaming in from multiple payment processors, and it's often arriving in these violent bursts.
That raw stream has to hit Cloud PubSub first. PubSub handles the decoupling and it absorbs those bursts. If a massive flood of fraudulent transactions hits the system, PubSub buffers the flow, and it ensures that the downstream processing pipelines aren't overwhelmed or crashed. It's the shock absorber.
Okay, next, we need to process those events instantly. We need to apply complex fraud rules, manage state. For instance, checking if a single user made 5 purchases in the last 10 seconds.
That is the crucial role of Cloud Data Flow. It takes that high-velocity stream from PubSub, it processes it in real time, it applies sophisticated windowing and session logic, which is all made possible by Apache Beam, to look at sequences of events. It can enrich the data with lookup information and ensure that required data quality and sequencing.
Okay, so once an event is processed and maybe flagged as potentially fraudulent, where does that data go?
It actually needs to serve 2 masters. Some of it, the operational lookup data, like those high-volume velocity checks or lists of known bad credit cards that need instant access.
That goes to Bigtable.
That goes to Cloud Bigtable for extremely low-latency operational lookups. Meanwhile, the structured, processed, and aggregated results, including the finalized flags for detected fraud and all the audit logs that get sent to BigQuery.
So BigQuery becomes the centralized store for all the historical analysis and for modeling future fraud patterns.
Exactly.
And the final piece, the interface. Where does the security team monitor and act on these fraud metrics in real time?
That real-time dashboard is powered by Looker, and it's using BigQuery as its primary source. Looker ensures that the metrics, like fraud rate or block transaction volume, are calculated consistently through LookML. This gives the security team absolute confidence in the accuracy of the live data they're using to make critical decisions.
Wow, that is a complete modern stack. PubSub for resilience and scale, Dataflow for intelligent real-time processing, Bigtable for operational speed, BigQuery for historical depth, and Looker for governance and visualization.
We've shown how each specialized tool plays a necessary and non-overlapping role in the pipeline. So we've covered the entire lifecycle today, and I really hope those critical distinctions are fundamentally clear now. Just remember that Dataproc is the path you take if you must scale existing Hadoop or Spark code with minimal change.
Right, and you can leverage those huge cost savings through preemptible instances for your batch jobs.
Whereas Dataflow is your choice for greenfield projects, or when you need that unified stream and batch processing, all built on that elegant serverless model provided by Apache Beam.
It just offers an architectural flexibility that Dataproc, which is tied to the Hadoop ecosystem, really can't match.
And we showed how BigQuery's power is only fully unlocked through meticulous optimization. Combining partitioning by date and clustering by a frequently filtered column like userid is the definitive strategy for minimizing those vast costs.
And crucially, that final layer of trust is imposed by Looker. It provides the semantic modeling layer, LookML, to guarantee that all analysis, whether it's operational or historical, is consistent across the entire organization.
And, we spent time detailing how BigQuery can access external data sources like Bigtable using federated queries, and how specialized tools like DataStream handle real-time database replication. This continuous effort to define logic over the data, rather than just moving the data around, it really points to a fundamental shift in data architecture.
Indeed. We've seen the rise of the data warehouse, then the data lake, and now we're seeing the rise of the data mesh, an idea focused on accessing data where it lives. The systems we discussed today are all moving toward the world where the defining architectural boundary is less about the physical storage and more about the interpretation layer.
So here's the provocative thought we want to leave you with. If the analytical engine, BigQuery, can query data across all these different physical locations, Bigtable, cloud storage, external databases, and if the business definitions, LOOKML, are managed centrally, are we witnessing the end of the traditional centralized data warehouse as the sole source of truth?
Or is the centralized data warehouse just evolving? Is it becoming less of a physical storage container and more of a unifying computational logic layer that transcends physical location?
The ultimate source of truth might be becoming the logic layer itself, regardless of whether the raw bytes reside in BigQuery or Bigtable.
Something to keep considering as these amazing technologies continue to integrate and evolve.
Until then, keep analyzing and keep optimizing.
We'll see you on the next deep dive.